So you got concavity nailed. The good news was you didn't have a lot new that you had to learn about that. You just had to kind of what? Apply this idea that the second derivative tells you about concavity. I got a key along here if you want to see it. So first questions on the 3-3 stuff. 51. Okay, let me get back there. 3-3, number 51. One of those, point of diminishing returns. Identify the point of diminishing returns for the input-output function. For each function, R is the revenue and X is the amount spent. The only thing I have to review for myself is in a diminishing returns problem, which function do you need? Is it the revenue? I just got to make sure. It measures, yeah, it seems like that equation is all set to go, from what I can tell. I was looking at the paragraph on page 197. They don't, I wish they'd come out and say a little bit more, but it says X is measured in dollars, Y is measured in output in dollars. So it's got to be revenue. Okay, so therefore the revenue equation they gave you, we don't have to do a profit thing or convert that in from demand or anything like that. All we have to do is go right ahead and what? Find the second derivative and find out when, if at all, the second derivative is equal to 0. Is that pretty much what you tried to do? Is that what you pretty much tried to do? A little difficulty doing that? Okay, let's see what's going on. So we've got the revenue equation is 1 over 50,000 multiplied by 600x squared minus x cubed. Okay, I guess they kind of set it up for you as a product, huh? So I suppose we could do it that way. So, and you know, to make this just a bit more self-explanatory, let's call this R of X. So we need to first find R prime of X. Product rule, the first times the derivative of the second plus the second times the derivative of the first. Well, the derivative of the first is 0, so do I even need to do that second part? No. So I don't need any more. Well, let's just go forward. What's R double prime of X? Okay, again, product rule. The first times the derivative of the second plus the second times the derivative of the first, which doesn't exist again. And so the question is, when will this equal 0? Well, you could just, what, multiply both sides by 50,000, and that just gives you this. Add 6x to both sides. 200. So it appears that that's the point of diminishing returns. And X again stands for, as they told you in the book, what? The amount spent on advertising. So in other words, if you spend up to 200 bucks, you're gaining. But if you spend more than 200 bucks, you're not. It's not really paying off. So don't spend more than 200. It seems like that's the ideal if you can afford it. So that should be dollars. Hopefully that agrees with the back. Yes. Uh-huh. It says, for each function, use a graphing utility to verify your results. I should probably have done that. But anyway, the point of diminishing returns. Okay, so I just found the x-coordinate of the point. So now I see their language. So what they're saying is, okay, first of all, where is that? And then, of course, we'd have to plug this in. Wow, you'd have to crank this out 200 squared times 600 minus 200 cubed and divide that by 50,000, and that would be this y-coordinate here. Now, why is there a second point? That's a good question. Is there anything in my algebra that I... I'm not sure. But what I'm going to do is, I don't know where a second point comes from at the moment, but what I'm going to do is let's graph this thing, and since they asked us to, let's take a look at it from that viewpoint. And it was, again, what? I'll just put it in this way, 600x squared, parentheses, 600x squared minus x cubed, and that whole thing is divided by 50,000. Okay, let's obviously zoom out. Now, whoops, the other way. Zoom out. Now, the whole idea here is we're supposed to be what? Finding, I don't know why I can't speak today. We're supposed to be finding these points of inflection are what we call these points of diminishing return. So here's the one we found at 200, and it appears it's at about what? A little bit over 300. Where's the other one? I'm trying to remember how to do this. Yeah, excuse me. I'm trying to remember. Oh yeah, grab the hand. Thank you. Well, the other, if we really zoom out far, I guess it's hard to tell. So what do they have for the other one? Oh, I thought you said there were two. They have two answers? Oh, so do you get where they get the second coordinate from now? You just plug it in and you find the, okay. So, and it appears that it's 200 comma, what, 300 something? Yeah. And that makes sense. There's only one point of inflection on this graph, right? Because this is forever concave up over here. Concave up, concave up, concave up, concave up, concave up. Switch over, point of inflection, concave down, and then forever. Yeah, so there's only one. Okay, good. That makes common sense, I'm glad. Yes.
Could you do 29?
I could. 29. Find the point or points of inflection. 29. I should go back. What was the page number on that previous one? I mean, not page number. That was number 51. Thank you. Okay. Now, 29, we have x minus 1 cubed. Multiplied by x minus 5. So, let me ask you this. How did you approach it? Did you multiply that out first? Did you use the product rule? Well, maybe I should try to use the product rules so we can kind of stay with your technique then. Okay, first derivative. Okay, the first times the derivative of the second. Well, that's just times 1, right? Plus the second times the derivative of the first. Unfortunately, not very short. I sure don't want to, yeah. I guess sooner or later we're going to have to start multiplying this thing out. And I guess now's the time. So let's see if you remember, our x minus 1 squared is x. Let me do this down on the, I need a timeout here. I got to do this on the side. X minus 1 squared is x squared minus 2x plus 1. And I need to take that times x minus 1 again. And that's x cubed minus x squared plus 2x squared. Whoops, minus 2x squared. Minus 2x squared plus 2x. Plus x minus 1. So that's x cubed minus 3x squared plus 3x minus 1. And then over here, wonderful, we got another one of these things. So we got 3 times this, which is 3x squared minus 6x plus 3 multiplied by 3, which is 9x squared minus 18x plus 9. And now all of that has to be multiplied by x minus 5. Probably doing this too quick, but anyway, here we go. 9x squared times x is 9x cubed. 9x squared times 5. Negative 45x squared. Negative 18x squared. Positive 90x plus 9x minus 45. Okay, so putting that together, what do I have? 9x cubed minus what? 63x squared, yeah. Plus 99x. And then we have minus 45. Okay, finally, adding those together gives me 10x cubed minus 66x squared. I really wish I could do this slower, but anyway, plus 3x plus that, plus 102x, and minus 46. Okay, I got to get rid of this stuff down below here now. Need the space. Okay, now we can do f double prime of x. If that's right, that would be 30x squared minus 132x plus 102. Now the question is, when is that equal to 0? So we're going to have a quadratic problem, and I'm going to divide everything through by 2 because I can divide both sides by 2. $66, right? Yeah. Plus 51. Are those all divisible by 3? Yeah. So I'm going to do a divide through by 3 now. Now, how do you solve a quadratic? Go ahead and use the quadratic. So, minus b plus or minus b squared, 22 squared, minus 4 times 5 times 17, all over 2a, which is 10. I'll let you go from there. You know, I'm a little worried. I went kind of fast up there on that expansion, but so the idea is find first derivative, find second derivative, set second derivative equal to 0, and then solve it. And it looks like we're going to get 2 solutions here. So according to this, I have 2 points of inflection that are going to come out of this. Yep.
How come you said the second one was 0?
Because they wanted you to find a point of inflection. And a fact that you got to nail is points of inflection always have second derivatives that are 0. So that's basically why I did it. It's kind of like, it's similar to, how do you find relative max and min? Oh, you find the first derivative and set it equal to 0. How do you find point of inflection? Find second derivative, set it equal to 0. Yep. Yes. 53. Find the production level that minimizes the average cost. So in other words, we need to use the cost formula. So again, there's no business horsing around where we have to multiply by x or figure out the profit. We're going to just use what they have there. Okay? And how do we find what did they say, minimize it? We got to find where the bottom of the parabola is. And so we have to find when the first derivative is equal to 0. Okay. So shouldn't be too bad. Here's our cost. Average cost, I guess. Do we have to convert that in any way? This is a business question now. Does anybody know? What do you have to do to cost to get average cost? Can you remember? Business people? It's got nothing to do with math. No? Nobody can? Okay, well then I'm just going to take this equation the way it is, 0.5x squared. You know we talked about this back about a chapter ago, but I just can't quite remember. What do you do to get average cost? Anybody remember? Take the cost. So I'm not quite sure how to answer that part of it, okay? If this is the average cost, then it's easy. But I'm not positive about that. I guess we'll find out real quickly in the back. Well, C prime of x is very easy to determine. And that can't be right because that makes no sense at all. The first derivative is what? You take 2 times a half, you get 1, so you get x plus 15. And when is that equal to 0? When x is a negative 15. And if x is the number of units, it doesn't make much sense. What is x? Yeah, it's producing x units. Well, then, if that's the case, I would say when you don't produce any. See, I think I'm missing the idea of what average cost is, and I'm just not remembering. Go ahead.
I was just gonna say that looking
Yeah, there's got to be something about finding average cost that I'm not remembering.
There's actually something in 3.5 about it.
There we go. But it should be something that had before, too, because let me see if there's anything before. If not, thank you for looking. Let's try an index under cost. No? How about average? Average cost function, page 211. Yeah, that's the one you're talking about. Well, what did I miss something in this section? Did they talk about average cost anywhere? Did anybody note? Well, let's look ahead at 211. Now, you do have to take the C equation and divide by x. So if you look at page 211, you see how you take the cost equation and divide by x in order to get the average cost? Okay. Why would they ask that question if we haven't? Seems to me we've talked about it, but I don't remember where, and the index is not pointing me in that direction. So, I don't know. So therefore, the average cost, according to page 211, is you take everything in the cost equation and divide it by x. Now you'd have to differentiate that, and that would involve a quotient rule over here. Okay? So let's do that. Let's see if that does it. So C, the average cost prime would be now quotient rule. Denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. So what is this? Negative, so it's 0.5 and then minus 5,000 over x squared. Now when is that equal to 0? Okay, so that would be when we cross multiply divide both sides by 0.5 10,000, and the square root of 10,000 is 100, right? How does that look for the answer? Now, I don't know where they. I'm a little upset with the book that they would ask you an average cost when I know we've talked about this, but it's been like 2 chapters ago, a chapter ago, long time. And then, so I don't quite know why they did that, but. So here's another one for your business file. When given a cost equation, how does one find the average cost? Answer, take the cost equation and divide everything through by x. It makes sense. Take the total cost and divide by how many. And how many is how many items you sold, x. So then go ahead and do what the book said. In this case, it said find the minimum. Okay, got to find the first derivative, set the derivative equal to 0. So the only thing holding us up here was this business stuff. Yep.
45.
45?
Probably relative max, but I have no idea how they have the inflection points.
Inflection points, find the second derivative, set it equal to 0.
Right, but I mean, just for this problem in particular, especially like, you're supposed to graph it.
No, you don't find inflection points by graphing. You could use it as a check, but you don't want to find them that way. No way. Oh, is that what they said? Oh my, I guess they did. Okay, my apologies. Normally this would not be a good technique, so I'll do what they said. Let's graph it, and I guess then you're just supposed to eyeball it. Okay, we can do that. So let's insert the function. 4 divided by 1 plus x squared. 4 divided by 1 plus x squared. Okay. I have no idea where we are. Is it? Oh yeah, there we go. Well, we can see we have inflection points because on the hump in the middle, it's obviously concave down, and over here, it's obviously concave up. So somewhere in between, like maybe about in here, is a point of inflection. So you would eyeball it and say, I don't know, maybe 0.8 for x, and over here, by symmetry, there's got to be another one right about at negative 0.8. So I think if that's what they wanted you to do. Now, did they want both coordinates? If so, then you would take 0.8, plug it into the function, and you could get your y coordinates. Yeah, when they say identify the points of reflection, I should know by now they want the x and the y coordinates. So eyeball the 0.8, stick her in, see what the y coordinate would be, and then just give its buddy on the negative side. Yeah. Yes. Where to start? We should probably talk about that then. In exercises 57 and 58, find the time t in years when the annual sales x of a new product are increasing at the greatest rate. Well, what does that mean? Increasing at the greatest rate. How do you find when a graph is increasing at the greatest rate? Let me ask you that question. Right, and how do you find that? So this is kind of weird. What we want is when the slope is as steep as possible. So all I can say is what I'd have to do is find the first derivative and somehow try to figure out a way to find out when that's as high as possible. Now how can we do that? Well, think about it. What happens when a slope is as high as possible? Okay, the curve is as much like this as possible. Of course, it can't be vertical. And what's going to happen right after you reach the high point? Isn't it going to have to start decreasing? So really what you're looking for is the inflection point. They could have come out and said that. If you're going to find a point of inflection, yes. So that was a sneaky way of getting you to think, hey, when is this as high as possible? Well, I know that right before it, it's going to be more like this, and right after it, it's going to be more, you know, it's going to be the other way. Oh, yeah, it's a point of inflection. And so that's what they were sneakily asking you to do there. And you're probably thinking, well, if they'd have said that, I'd have known what to do. Yeah. We got to go. We got to move on. So let me, here's the lesson 3-4. Oh, the good news is this is not exactly new stuff. I mean, you've been finding relative mins and max. Where are the top and the bottom of curves? Well, you know how to do that. Find the first derivative and set it equal to 0. So I have good news. I mean, the techniques are going to be not going to be new. What's going to be new is how the problems are worded. So everybody, take a look at question 2 at the end. Going backwards again today. And that's because you already know these techniques. These are little word problems. And we got to solve them using our knowledge of calculus. Actually, let me just start a fresh page for this instead of doing this cover-up thing. Okay, the sum is S and the product is a maximum. Well, for the moment, let's just say we have two numbers who add up to the sum S. Okay, you're supposed to find two positive numbers that add up to the highest. You know, what are the two numbers that add up to S, and when they multiply, they give you the highest result? Okay. The problem is we have too many letters here. So what we could do is, instead of Y, I gotta think, is this what we want to do? Let me go back to my slide, I guess. Okay, so when you add them up, you get S, the sum. And just like I did a second ago, can't we call, here I solved for X. Isn't X another name for X, just S minus Y? And is, or we do it this way, isn't Y just S minus X? Okay, now take the two numbers, X and S minus X, so I don't have, and multiply them together. Because remember, the idea was you were supposed to get a product that's as high as possible. So I got to multiply them. Well, what do I get when I multiply them? Sx minus x squared. Okay. Well, where's the high point of that? Well, good news for you. Something that has a minus x squared is a parabola that opens downward, and it will have a high point. By the way, they're not going to throw you for a loop and go, you know what? I'm going to give him a parabola that looks like this. And I'm going to ask him to find the low. And then go off in the corner and chuckle. Ha ha, let's see him try to find the low of that. Because there is no low. No, we're not going to do that. Okay? So here they're saying, find the maximum. And sure enough, what is this? Anytime you have a parabola with a minus x squared, what does that mean? It opens like this, and it really does have a high point. Okay, cool. I just want to know what the high point is. So how do you do that? In calculus, you find the derivative, and you set the derivative equal to 0. So I did that. Negative 2x plus s, set it equal to 0, and look at the result I got. Head's in the way? Sorry, I can't get it any higher. I guess I could. There we go. Then you can't see the whole thing. But anyway, I came up with x being half of s. All right, now think about it. Two numbers add up to s. And I want to know how I get the best results for the highest product. And I found out that the first number has to be s over 2. By the way, if that's what x is, what's y? Go back to the top. If x do it right here. If x is s over 2, think of this as s over 2, what does y turn out to be? What's s minus a half of s? A half of s. So in other words, x and y both turn out to be a half of s. They're equal. Sure enough, try it. Take a number like 10. Think of two numbers that when they add up to 10. I mean, just take the whole numbers. 9 and 1, 5 and 5, 3 and 7. Which ones, when you multiply them, come out to the highest product? And this problem said, oh, well, that's easy. It's 5 and 5. When each number is half of the original total. Sure enough, try it. 5 times 5 is 25. Do you find any other product that's higher of your numbers? Like what's 8 and 2? 16. What's,
It was close.
what's that?
It was close.
It was close. Yes, I would agree it was close. Well, what are some other ones? 9 and 1. 9. 7 and 3. 21. Even closer.
6 and 4.
6 and 4 is better. And what's the very best? 5 and 5. Yes. I was just trying to capitalize on your close. Yes. This is true. Close is true. So what did we get? So we just found something out. If you ever get a problem where they ask you to add two things up to some total, how can you get the maximum product? Answer is, always just take the two that are equal. It'll give you the top every time. So calculus just told us that. Here. Let's go on and do another one. Number 8. The difference, now this is not a sum, so this is a different ballgame. The difference of two numbers is 50. So after you subtract two numbers, the answer is 50. Okay? And it goes on and says, find the two numbers such that their product is a minimum. So this time I don't want the highest number, I want the lowest. Okay, well, I did a little substitution. Let's call x 50 plus y. Just adding y to both sides. Okay. Then when I multiply the two numbers, y and 50 plus y, I get this polynomial. Now I set it equal to 0. Oh, by the way, take a look at the polynomial. This time it's y squared plus 50y. Is that a parabola? Yep. And, I mean, you normally think of them as being x's, but don't let that bother you. And the fact that the thing in front of the x squared is positive, what does that tell you about our parabola? Instead of opening down, doesn't this one open up? Okay, now if you have an upward opening parabola, do you really have a minimum? Yeah. So again, do you see how they didn't go off in the corner and go, oh, we're asking them to find a minimum, and there is none. There will be. Yeah.
So for the y or the x and then you...
It doesn't matter.
Oh,
I could have done, yeah, it's a good question. I could have just said, hey, let's solve for x. And then we could have used x, we could have used, x and whatever that x then turned out to be. So we could have done it that way. It really doesn't matter. So yeah, I'm glad you brought that up. I should have stated that. So anyway, you all see how I got to here. Now, easy job. Find derivative. Set derivative equal to 0. Solve. Y equals negative 25. Well, if y is negative 25, then what's x? Actually, the easiest way is to do it right here. If y is negative 25, then what's x? Positive 25, right? And if you multiply those two numbers, what do you get? What's 25 times negative 25? It's negative 625. You're going to find that that's the lowest number you can get. Notice the numbers are still kind of equal, but the signs are obviously opposite here. So we're starting to see a pattern. Try any, you don't have to try other combinations because calculus has told us that's the lowest. Okay. Let's try one that actually has words in it. Number 18. This is a fairly typical calculus problem, by the way. I have seen this in just about every calculus book I've seen, and there are lots of calculus books that do this very frequently. An open box is to be made from a 6-inch by 6-inch square piece of material by cutting equal squares from the corners and turning up the sides. So in other words, in that picture in the book, if you cut out the white squares in the corners, you literally had a tin snip or whatever, and you cut those corners out, then couldn't you lift the sides up and fold along the dotted lines and kind of make yourself an open box? Does everybody see that? Okay, the idea is, how can you do that and get the box with the greatest volume? So the question is, how big should X be so that I get the tallest possible, not tallest, excuse me, the most volume in the box? You see, we got a problem here. If we make X really tiny, that'll make the bottom of the box bigger, but then what happens to the height of the box? Dinky, right? Okay, well, what if I make X bigger? Well, that'll make it taller, but it makes the bottom smaller. So do you see how you got a give and take here? So it's not just a real, somebody else, that's simple, just cut out everything, and then, you'll have a really, really tall box, yeah, with zero base. Of course, that doesn't give you any volume. So it's got to be somewhere in between. Okay, so there's our concept. Let's, as you can see, they drew this partly for us here. Let's see, we need a square. And we've cut some corners out here. So we cut out a corner. We do that in all four corners. So, and then I won't draw the fold lines in, but you can see how that would work. Now, if this is 6 all the way from here to here, and this little guy right here, from here to here, is X, then doesn't this have to be six take away an X on both ends, 6 take away 2X? Okay, and doesn't this also have to be 6 minus 2X? I don't know what I'm doing with the takeaway. No kindergarten today. Okay. All right, so does everybody see that the bottom of the box would be 6 minus 6 take away 2X times 6 take away 2X? And then how high would the box be? Wouldn't it be X? So, how do you find the volume of a rectangular solid like that? Don't you take length times width times height? So it would be length times width times height. Does everybody see that would be the volume? And now the whole idea is to get this thing to be as big as possible. Well, we probably need to multiply it out, don't we? So here we go. 6, let's do this part first. What's 6 times 6? 36. 6 times minus 12x, and another one is minus 24x plus 4x squared. And finally, when I multiply through by x, I get so there's the volume of this thing. Now, how can I get that to be as big as possible? Answer is I need the first derivative to be equal to 0. So I'm trying to find where the high point is there. So I need to find v prime. pretty easy. Now, 12x squared minus 48x plus 36. Now, when will that be equal to 0? Can't I divide that whole thing through by 12? Do you notice they're all divisible? So 0 equals x squared minus 4x plus 9. Hey, is that factorable? No. It's close, but it's not. So I got to use the quadratic. All right. So x equals minus b plus or minus. It's 3 and it's factorable. Thank you. So are you telling me 36 divided by 12 is 3? Yeah, you are correct. Very good. I was still working on my takeaways. This should be a 0. So what is the factorization? Minus 3 minus 1, huh? That makes sense? And so, when are these equal to 0? When x is 3 and when x is 1. So are those both solutions? No, why not? Why is x minus 3, even though I did the math correct thanks to your help, why is that not a legitimate solution? Just go back to the original problem. What if you cut out 3-inch squares from each corner? You have no bottom left. So that obviously is not going to give you, so that even though we did the math correctly, here's where you got to do a visual, you got to go back and check. And then, because the math is right, it doesn't fit the problem, I have to reject it. But there's a legitimate answer. If I cut 1-inch squares out, now I'm going to get a bottom, and I'm really going to have a height, and I'm really going to have a volume. What's the final thing asked in number 18? Okay, now we're not done yet. I found the dimension of the best cutout. But what is the volume? Let's figure it out. Well, where is it? Right here. I'm just going back and copying my V equation that I did before. What happens when x is 1? Sorry, that's not right. 36 minus 24 is 12, and 12 plus 4 is 16. And I forgot, what were those? Inches. Okay, so finally, what's the biggest volume you could get? There it is. So do you see how we're just using the same stuff we've learned all along? Okay, now we need to find our task. One to 23, the odds. Yeah, and then do the other, every other. You can do them that way if you'd like. You guys are hilarious.